Hello everyone. In today's lesson, we will be discussing limits at infinity. Let us begin with an informal definition. If the values of f of x become arbitrarily close to L, as x becomes sufficiently large, we say the function f has a limit at infinity and write lim x approaches infinity of f of x equals L. If the values of f of x becomes arbitrarily close to L for x less than 0, as absolute value of x becomes sufficiently large, we say that the function has a limit at negative infinity, and we write limit x approaches negative infinity of f of x equals L. Now here are some important facts that you should know about limits at infinity. 1. If r is a positive rational number and c is a real number, then the limit as x approaches infinity of c over x raised to the r is equal to 0. And the limit as x approaches negative infinity of c over x to the r equals 0. The second limit is valid when x to the r is defined when x is less than 0. Another way you might see this fact stated is many times you will see a 1 instead of a c. So sometimes when we're doing our solutions, we pull the c in front of the limit and then put 1 over x to the r and make that 0. So it's exactly the same idea. About exponential functions, 2. Limit as x approaches infinity of e to the x is equal to 0, and limit as x approaches negative infinity of e to the x equals 0. 3. The limit as x approaches positive infinity of e to the negative x equals 0. The limit as x approaches negative infinity of e to the negative x is equal to positive infinity. About radicals, absolute value of x is equal to the square root of x squared for all x. Absolute value of x is equal to x when x is greater than 0. Absolute value of x is equal to negative x when x is less than 0. Let's look at a numerical example. Given f of x is equal to 2 plus 1 over x, complete the following table, then sketch a possible graph. We have x and f of x, and numbers 10, 100, 1000, and this should really be 10,000. So we're going to treat the last one as 10,000. And then x and f of x, limit as x approaches negative infinity, and negative 10, negative 100, negative 1000. And then that should be negative 10,000. Here, using your calculator, you can fill out the table. And notice here that when x is 10, f of x is 2.1, x is 100, f of x is 2.01, x is 1000, f of x is equal to 2.001, and when x is 10,000, f of x is equal to 2.0001. You notice a pattern here. The limit as x approaches positive infinity of f of x is equal to 2. It's going closer, getting closer and closer to 2. Now, on the other side, we have x at negative 10, f of x is 1.9, x at negative 100, f of x is 1.99, x is negative 1000, f of x would be 1.999, when x is negative 10,000, f of x is 1.9999. So there, our observation is that the limit as x approaches negative infinity of f of x is also equal to 2. About horizontal asymptotes. If the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L, we say that the line y equals L is a horizontal asymptote. So once you take the limits, it's approaching specific number as we approach infinity, then we have a horizontal asymptote. So when computing limits at infinity, we continue to use the laws of limits that we previously met. For rational functions, what we do is that we divide each term of the expression by the highest term in the denominator. The denominator is the highest degree or highest term of the. Okay, so we think of the variable and look for the highest degree. So find the limit as x approaches positive infinity of 2x minus 1 over x plus 1. The highest degree of the variable x here is 1. So let's solve that. Okay, so we have the limit as x approaches positive infinity of 2x minus 1 over x plus 1. What we do here, we divide each term in the denominator, each term in the entire expression by the highest exponent in the denominator. So we divide in each term by x. So we go down to our next step. And so we divide this 2x by x, this minus 1 by x, this x by x, and this. That should be a plus 1 here by x, right? So check the sign right here. It should be a plus 1. And now if you continue working that down, the 1 over x's, as x gets to infinity, the 1 over x goes off to 0. 2x divided by x will just become 2. X over x is 1. This other 1 over x goes off to 0, whether it was a plus or minus. It really should be a plus. It goes off to 0 as well. So you're left with 2 over 1. Limit as x approaches infinity of 2 over 1 equals 2. Let's consider another problem. Given f of x is equal to 5 minus 2 over x squared, find the limit as x approaches positive infinity of f of x and the limit as x approaches negative infinity of f of x, and identify any asymptotes. Okay, so there are two sides. You want to do the limit as x approaches positive infinity of 5 minus 2 over x squared. Again, we can use one of the laws of limits to separate this into two separate limits. So that would be a limit as x approaches positive infinity of 5 minus the limit as x approaches positive infinity of 2 over x squared. And so a limit as x approaches anything of a constant is just that constant, minus here we have pulled the 2 forwards, even though it's by the law that we had, we don't necessarily have to do it because it's still going to go to 0 regardless. But you can, by another limit law, pull that 2 in front. And so that's 2 times the limit as x approaches positive infinity of 1 over x squared. Notice this 1 over x squared is going to 0. And then we have 5 minus 2 times 0. And that would give us 5 minus 0, which would be equal to 5. On the other side, limit as x approaches negative infinity of 5 minus 2 over x squared. We do the same thing. Apply the limit laws. And limit as x approaches in negative infinity of 5 minus the limit as x approaches negative infinity of 2 over x squared. And then that would be equal to 5 minus 2 times limit as x approaches infinity of 1 over x squared. That goes off to 0. The 1 over x squared goes off to 0 as x approaches negative infinity. And so we have 5 minus 2 times 0. 2 times 0 is 0. So that gives you 5. So on both sides is approaching 5. So f has a horizontal asymptote at y equals 5. It could be either or, as long as it's approaching a specific number from either side. And the sides, it doesn't have to be the same number either. But in this case, it is the same, so that's good. The function has a horizontal asymptote at y equals 5. Let's talk a little bit about the behavior of polynomial functions. The end behavior of a polynomial function is determined by the highest degree exponent of the function. If the highest degree n is even, then the limit as x approaches infinity, f of n is x to the n, is equal to positive infinity, and the limit as x approaches negative infinity of x raised to the n is equal to positive infinity. So if you can think about, let's say a y is equal to x squared as a model for this, then notice that both on the left side and on the right side, your graph will be increasing towards positive infinity. And so, as a visual, you can think of that. And then if the highest exponent n is odd, then the limit as x approaches positive infinity of x to the n will be equal to positive infinity, and the limit as x approaches negative infinity of x to the n will be equal to negative infinity. And as a visual for this, you can think about your graph of f of x is equal to x cubed. And also, in these cases, you have to also think about if you have other things affecting what is happening apart from just the standard. You have to think about transformations as well. Alrighty, so question: in each of the functions below, evaluate the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. So in this case, in our example, f of x is equal to negative 5x cubed. F of x is equal to negative 5x cubed. So in this case, f of x is equal to negative 5x cubed. We have to think about, or we should think about, our original function, or parent function f of x is equal to x cubed, and try to reason out what is happening in this case. So what does the 5 do to it? What does the negative sign do to it? And what is the exponent telling us about it? So the negative 5 gives you, the 5 gives you a vertical stretch of the function, and the negative sign flips the original function. So total, the negative 5 would give you a vertical stretch and a flip over the x-axis. Okay, the 3 in the exponent tells us about the original n behavior, and if it was on the positive side, it would have been going up to positive infinity, and the negative side would be going to negative infinity, but we're flipping them around by a reverse of it over the x-axis. So let's see what's happening here. It says the limit as x approaches positive infinity of negative 5x cubed is equal to negative infinity, and the limit as x approaches negative infinity of negative 5x cubed is equal to positive infinity, because it flips the direction of the original function. Okay, so that is our answer right there. And if you graph it, you can graph it to verify it as well. Okay, alrighty. Let's look at another problem. We want to try to find the end behavior of this function. F of x is equal to 3x squared plus 4x all over x plus 2. So let us look at the behavior of the function as x approaches positive infinity. The limit as x approaches positive infinity of 3x squared plus 4x over x plus 2 be equal to the limit as x approaches infinity of 3x plus 4 over 1 plus 2 over x. What we did here is that we divide each term by x. Right? Divide each term by x because x was the highest power. X to the 1 was the highest power in the denominator. And so doing some algebra here and noting that the 3x itself approaches infinity and the 2 over x approaches 0. So what we are left with is 3x plus 4 over 1, which will be 3x plus 4. Eventually that's going to be infinity over 1. And so the answer there is infinity. On the left side, the limit as x approaches negative infinity of 3x squared plus 4x over x plus 2. The algebra is the same, except that we differ when it comes to what values we are using for x. And since we're using negative values, then your 3x will be approaching negative infinity. 1 is still just 1, so we have negative infinity over 1. And finally, our answer is negative infinity. So that's the behavior at infinity.